Diamonds are a maths teacher's worst nightmare. A professional learning session focused on two-dimensional space in the kindergarten to Year 6 classroom. By the end of this session, I hope that you will be able to understand the importance of geometry in the kindergarten to Year 6 classroom, consider some of the challenges with teaching and learning two-dimensional space, identify effective practices in the teaching of geometry, and explore a range of resources to support teaching and learning activities. This image was shared on a popular social media group for teachers, and the question was asked, "What shape is this?" What would your answer to this question be? The answers given by the teachers in this group may surprise you. 78 teachers responded to this post, with just over half identifying this as a square. The second most common answer was diamond, which is not a two-dimensional shape. Why do you think this question is so challenging?
It's important to acknowledge that geometry, and in particular 2D space, can be a challenging subject for many people. Let's consider some of the reasons why.
For all its practical considerations and applications, geometric objects are not real objects. They are ideal objects. A perfect circle, triangle, or square does not exist in the real world. They are purely abstract. The names of shapes, their definitions, and their classifications can be difficult and confusing for many people. For example, the names of polygons such as pentagon, hexagon, octagon, and so on is fairly systematic. This is due to their Greek origins, with gon meaning knee and so referring to the number of angles. However, it doesn't apply to the 3- or 4-sided polygons. They are not trigons and tetragons, but triangles and quadrilaterals, with lateral referring to the side and quad stemming from the Latin name for 4. The definitions of shapes can be confusing, partly given that any definition often relies on a knowledge of other terms and definitions. For example, a square can be defined as a quadrilateral with equal sides and 4 right angles. To interpret this definition, one needs to also understand what a quadrilateral is, a right angle, and even a side. In addition, the classification of shapes can be confusing. For example, a square is not only a quadrilateral, but is also a special case of a rectangle and a rhombus. All of these factors are important to consider when thinking about the teaching and learning of geometry in the primary classroom.
So how much time should we be spending on geometry in the primary mathematics classroom? The answer to this is not as straightforward as you might think.
The New South Wales K-10 mathematics syllabus is divided into 3 strands: number and algebra, measurement and geometry, and statistics and probability. The grouping of measurement and geometry, though seemingly different aspects of mathematics, is deliberate. It seeks to emphasise the relationship between the 2 strands and encourage teachers to explore the connections between these areas. The measurement and geometry strand is then broken into a further 9 sub-strands, the most of any of the strands of the syllabus. 4 of these sub-strands relate to geometry: two-dimensional space, three-dimensional space, angles, and position. Although in New South Wales the amount of time to be spent on mathematics teaching each week is outlined by the New South Wales Education Standards Authority, there is no breakdown of how much time should be spent on each of the strands of the mathematics syllabus. This may come as a surprise. As Attard has observed, this may be due to a perceived intent of the curriculum, where number is viewed as the most important part of the mathematics syllabus. It may also reflect the way we experience the curriculum as students. As a result, there is a large focus on the number and algebra strand in the primary mathematics classroom, while the teaching of other strands, such as geometry, can be minimised, or even worse, largely ignored. Perhaps one of the reasons for this imbalance may also be the increased teacher accountability through standardised testing. Logan, Lowry and Scriven have noted that this has increased attention on the number content of the curriculum. However, while acknowledging that NAPLAN is only one measure of student knowledge and achievement of mathematics and numeracy, it is important to recognise that around half the questions in NAPLAN rely on graphics and therefore visual and spatial reasoning skills. This is not a trick, but rather a reflection of the importance of these skills in developing numeracy skills. As such, it is more important than ever to allow students to engage with the practical affordances of learning in geometry. The good news is there are lots of reasons even more important than standardised testing for why increasing the amount of time spent on geometry benefits students. Many studies have demonstrated the connection between geometry and number concepts. In the primary school, these can be particularly helpful for students in constructing their understandings in number and algebra. Geometry's practical nature promotes advanced mathematical reasoning. Due to its link to the development of spatial sense, geometry provides the basis for acquiring advanced mathematical knowledge in the STEM areas of science, technology, engineering, and of course, mathematics. Prominent physicists Einstein and Hawking attributed their advancements to geometry. Both emphasised how they thought about their ideas and concepts in terms of geometry first and then the numbers later. Clements and Sarama argue that spatial and geometric thinking are essential in developing thinking around number and arithmetic concepts and skills. In addition, they are themselves important skills, and there are some ideas, such as the representation of magnitude, that are dependent on these systems in the brain. Without geometry, these skills do not have the chance to develop. For some students, pen and paper-driven mathematics experiences can be frustrating and difficult. When spatial reasoning is emphasised, these students experience success, sometimes even greater success than some of the higher performing peers.
Now would be a good time to reflect on your own scope and sequence. How much time is given to geometry across a term? Is it just 2 days a week, a few weeks a term, or perhaps in the last few weeks of term, after all the number content has been covered? Recognising the benefits of spending more time on geometry is a great starting point. However, as many teachers know, just spending more time on a concept won't necessarily improve student learning in this area. This can only be achieved through the provision of realistic and challenging learning experiences. So how should we do this?
The Van Heel model describes the progression of thinking in geometry. It describes the thinking processes at each level, not the content. The levels are visualization, descriptive or analysis, informal deductions, formal deductions, and rigor. Students may be working with more advanced content, such as Stage 2 or Stage 3 syllabus content, but still be operating at lower levels of thinking. Levels 1 to 3 particularly apply to the primary mathematics classroom. Level 1, students focus on the appearance of a shape. There is little attention paid to its properties. For example, a student may recognise a square because it looks like a box. However, once it is turned, like in the second shape, they may be confused, such as in our opening question, and think it is a different shape altogether. When examining the third shape, students may name it as a parallelogram, but explain that they know this because it looks like a pushed over rectangle, not because of any of its properties. At level 2, students begin to notice and describe the properties of shapes. They can identify a square because it has 4 equal sides and 4 right angles, for example. When students work at level 3, they begin to see the relationships between properties and shapes. The shape above would first be categorised as a quadrilateral because it has 4 sides, then as a rectangle because it has 4 right angles, and then finally as a square due to the equality of the sides. Level 4 is more applicable for high school students. Students move beyond making deductions using known facts or using a known theorem. They see the relationship of the properties of a shape. For example, students can prove angles are congruent by using a knowledge of angles and parallel lines, or prove Pythagoras' theorem. Level 5 is typical of university-level geometry. Students at this level prove and disprove things, testing ideas using their knowledge of geometry to prove things about them.
Van Heel's model provides a helpful framework for organising teaching and learning activities that promote geometric thinking as well as the geometric knowledge of the syllabus. Many of the resources and learning activities that are commonly used in primary mathematics classrooms are useful for achieving this. However, it is also important to acknowledge some of their limitations and how these can be overcome. Sometimes simple adjustments to current practices can ensure that students do not become stuck at lower levels of geometric thinking.
When determining what teaching and learning activities will effectively promote the development of higher levels of geometric thinking, there are several key considerations. First of all, the role of discussion and explanation cannot be emphasised enough. This serves the purpose of sharing thoughts and ideas, but also supports the development of the technical language that is necessary for higher levels of geometric thinking. It is true discussion between students and teachers that allows this to happen, not just students listening to teachers. When eliciting a response to the name of a shape, teachers move beyond reinforcing what the student already knows, such as its name, and to developing student knowledge. Asking a student how they know a shape is a triangle, square, or rectangle not only reveals their level of thinking, but can provide the opportunity for instruction to take place. Practical investigations, including those in the form of unstructured play, allow students to explore, challenge, and reason about ideas. Both informal and formal opportunities should engage and challenge students and encourage them to consider more complex ideas. This is true for students up to and beyond Stage 3, not just those in the younger years. As students build their understandings, then they can move to more abstract activities. One crucial factor that was highlighted in a study by Hourigan and Levy is the importance of students having experience with non-prototypical shapes. Prototypical or stereotypical shapes are like those on the left. They often take the form of regular polygons, those with equal sides and equal angles. Non-prototypical shapes, or irregular shapes, are like those on the right. This group features a triangle, a hexagon, a pentagon, and a decagon, just like the group on the left. However, many students may not recognise this. Students who only experience prototypical shapes, such as those in pattern block sets, may rely solely on the appearance of a shape to identify it, rather than its properties. That's because they have never had to do anything else. It is only through engagement with non-prototypical shapes that students will develop the skills to move beyond the visualization level that relies on the appearance of such shapes to higher levels of thinking where students interpret them using their knowledge and understanding of their properties. Perhaps these look familiar. Pattern blocks are prototypical examples of two-dimensional shapes and are commonly found in primary classrooms. They offer students the benefit of making a two-dimensional shape more tangible by providing the opportunity for them to handle and manipulate them. However, they also have some limitations. First of all, technically, they are three-dimensional objects. This can be problematic for many students if we are trying to encourage them to see shapes from different perspectives. In addition, as prototypical examples of shapes, an over-reliance on them may lead to reliance on visual appearance when identifying shapes. However, they can still be extremely valuable. As they can be manipulated, students can investigate shapes presented in different orientations, including a square and an equilateral triangle. These are often only presented with a flat base at the bottom. They also offer a rich opportunity for students to explore the properties of shapes when they are used to construct other shapes. For example, how could you use the blocks to build a hexagon? or a triangle? What other shapes could you build and name? This can be an engaging and challenging task for students right up to Year 6. Using them in digital form also unlocks further opportunities for manipulation while reinforcing the fact that the students are dealing with two-dimensional shapes rather than three-dimensional. Conducting a shape hunt is a popular learning activity. It allows students to experience everyday examples of shapes in their environment. One problem with this can be that the frequency that some shapes occur, such as squares, rectangles and triangles, and the infrequency of others, including circles and polygons such as pentagons, hexagons and octagons. Additionally, it can serve to only reinforce a visual level of thought. By emphasising properties, students are encouraged to be more descriptive and use more deductive levels of thinking. It also offers the potential to consider non-prototypical examples of shapes that are more prolific in the environment than their pure abstract forms. As such, when supported by conjecture, explanation and discussion, a shape hunt can be an extremely rich learning experience. When looking to provide non-prototypical examples of two-dimensional shapes, either as a manipulative or in an abstract form such as a printed worksheet, there is no need for sophisticated or expensive resources. They can easily be created with word processing software. The Shapes Insert tool allows for a large range of shapes to be created, both by teachers and the students themselves. They can then be investigated by printing them off so that students may physically handle them, or by inviting students to manipulate them digitally. The GeoBoard in its physical and digital form is also extremely useful. It offers students the chance to manipulate two-dimensional shapes while avoiding confusing them with three-dimensional objects. Utilising both sides of the GeoBoard can also encounter non-prototypical examples of polygons. Challenge students to make different examples of shapes and justify their creations. Rebecca Sear highlights how useful the simple task of paper folding can be. It is both accessible and challenging, with the focus on the critical development of student language rather than complicated resources or tools. On the UCubed website, there is a variety of paper folding tasks, many of which are suitable for a broad range of students. In the shape origami task, for example, students use a standard A4 sheet of paper and fold it to make a smaller rectangle, a triangle, or a square. They must convince others that the shape they have made is the one required. This can be extended in a limitless number of ways, not only with different shapes, but by starting with different pieces of paper, such as a square piece or even a circle.
Improving the quality of teaching and learning activities we offer students is fundamental to improving student development and achievement in geometry. However, the most significant step that all teachers can take is to see geometry as a topic that intersects with the other aspects of mathematics, not just as a standalone topic.
Here are just some of the connections that two-dimensional space has with other areas of the New South Wales K-10 mathematics syllabus. For example, when discussing two-dimensional shape properties, we inevitably need to talk about length and angles. As we compare them in different ways, the focus may include the area of the shape. When manipulating shapes in different orientations, we may describe these changes in position using the fractional language of quarter and half turns. Geometric patterns, including square and triangular numbers, are fundamental to early algebra. You may know of others that you would like to include. By recognising the importance of connecting mathematical concepts, including geometry, not only can we begin to address the time pressures faced in the delivery of the curriculum, but we can appreciate the importance of geometry not only within the classroom, but in everyday life. Let's return to our original question and the answers provided. Has your perspective changed on any of the answers given, or perhaps even your own answer? Perhaps these could provide a valuable discussion with the staff and students in your school. because in the end, the more we can encourage mathematical discourse in schools, the more we will all benefit.